Let's look at another example. So we've got these four vectors here, and the question is, are the vectors linearly independent? Is there redundancy here that we could remove? And because I have linear algebra superpowers, I can look at these four and already tell that they're dependent. You can't do that yet, but before the end of this video, you too will have this linear algebra superpower. You will get bitten by the radioactive spider of Theorem 8. But in the meantime, since you don't have that power yet, let's go ahead and do this the old-fashioned way, which is just to say we're looking for a non-trivial solution to the homogeneous equation. So pretend these are four vectors in a vector equation that's going to be equal to 0, 0, 0. And we'll go ahead and do the row reduction. We already know there is the trivial solution. There's already one solution. But if there's a free variable, if there are more solutions than just one, then we'll have linear dependence. So make sure you didn't miss that. Let me say it again. If there's a free variable, then we have infinitely many solutions, which means there's more than just the trivial solution, which means there's linear dependence. Okay, so once we do row reduction here, I can see there is a free variable, and there will be linear dependence then. And without diving too deep into it, this -9, -4 is enough for me to know that, see if I can jam this in here, -9 of that minus 4 of that should equal that. There's your linear dependence. Let's check that just to make sure it's true. So -9 times 1 is -9. Plus 12 is +3. That would, second row, be +27 minus 28 would be -1. And third row, 0 minus 4 is -4. Okay, so there's a linear dependence relationship amongst these vectors. And again, the superpower is not doing row reduction in your head, by the way. It has nothing to do with looking at this stuff over here at all. But let's go ahead and get Theorem 7, which is not the superpower, and then we'll get to Theorem 8. So Theorem 7, again, is just the book's way of saying what we already know, which is basically a set of two or more vectors is linearly dependent if and only if at least one of the vectors is a combination of the others. Okay, and we just figured that out. -9 of this vector minus 4 of that vector is equal to that vector. So there's our one vector that's a combination of the others. And it says if S is a linearly dependent set, then some vector is a combination of the preceding vectors. So the third one was a combination of the first and second ones. The main reason I wanted to look at Theorem 7 right now is actually for the warning that comes after it. Theorem 7 does not say that every vector in a linearly dependent set is a combination of the others. It's possible to have a dependent set like the one that we have right here and have at least one vector in there not be a combination of the others. In this particular case, it's true that the fourth vector cannot be produced by combining the previous three. And I can tell that looking at the row reduced form here, which, again, I don't expect you to exactly have all those skills yet, but let me give you a more trivial example here of, I'm going to write down a linearly dependent set of vectors. So here's my new example. Let's go 1, 0, 0. 0, 1, 0, 0, 0, 1, and 0, 1, 1. And if it's not clear, hopefully you'll notice that 1 of the second vector plus 1 of the third vector equals the fourth vector. So there's a dependence right there. So this set of 4 vectors is linearly dependent set of vectors. However, hopefully it's also fairly clear that there is no way to produce the first vector from the other 3. Right? The other 3 all have a 0 in the first spot. There's just no way to combine them and get a 1 here. So it is not true if you have a dependent set that every single vector is dependent. It just means that at least one of them is. Okay, so good enough on that. Let's go ahead and get to the magic. Let's get to the superpower theorem, Theorem 8. Theorem 8 says if a set contains more vectors than there are entries in each vector, then the set's dependent. So let's unpack that a little bit. If a set contains more vectors than there are entries in each vector. So look at our first example here. There were 3 entries in each vector. 3, 3, 3, 3. Okay, so there's 3 entries in each vector, but we had more than 3 vectors. We had 4. So the set contained more vectors than there are entries. Then the set has to be linearly dependent. And if you think about that a little bit, anytime you have a set of 4 vectors and 3 that are 3 dimensions each, so anytime you've got something that looks like this, and then you're trying to solve. Think about what happens when you row reduce this. How many pivots can you have? Right, at most, you can have 3 pivots. You can only have 1 pivot per row. So at most, you'll have 3 pivots here, but there's 4 columns. So that means there's going to be 1 free variable. And as soon as there's a free variable, there's linear dependence, right? Because there's ways besides the trivial to make these vectors come out to 0. So the same thing's true if I have so far I'm okay, or at least I could be okay. These are 2-dimensional vectors, but as soon as I throw a 3rd one in, I am guaranteed that I now have a linearly dependent set. There's some way to combine 2 of these vectors to produce the 3rd one. I don't know exactly what it is. Given that I just made this up, it probably involves horrible fractions. But there is a way. If I augment and row reduce, if I row reduce that, at most there's going to be 2 pivots. There's going to be a free variable. There will be multiple solutions besides the trivial solution to this one. So that's how I was able to look at our starting example right away and just say, hey, there are 3-dimensional vectors here, but there's 4 of them. That's too crowded. There's too many of them. It's going to be linearly dependent when I row reduce. I just want to put one other little idea, one other shortcut in your head. I won't exactly call this one a superpower because it only works in one particular instance, but it's worth noting as well. So if the 0 vector is in the set, the set's automatically dependent. Okay, so 2-dimensional vectors, I've only got 2 of them, so I'm not violating Theorem 8 here. But with the 0 vector present, I can automatically say that 0 of this equals that. And if there's more vectors, you can just say 0 of all of them makes the other one. Or if you really want to do the homogeneous version, you can say 0 of that plus 1 of that, or whatever else you want, equals 0, 0. So anytime the 0 vector is in the set's linearly dependent. you can always write 0, 0 as a combination of other vectors, right? Just take 0 of all the other vectors, and you will indeed produce the 0 vector. Okay, so I think that's it for this video.